My name is Marek Vasut, and I'm going to talk about safe update of firmware blobs in bootloader stack today. I'll split this talk into 4 sections. First section, I'll talk about what the bootloader stack actually is, what is it that I mean by that. Then I'll move on to porting U-boot SPL. Then I'll talk about starting OpTee-OS from U-boot. And finally, I'll talk about Falcon boot mode, which is potentially interesting for deployments where security is important. First of all, bootloader stack. So bootloader stack is everything, all the software that runs from the point where you power on your system all the way until the operating system kernel takes over. This is the whole software stack that's in there. The bootloader stack used to be very simple. It used to be a single program in general, which was running from some sort of a memory-mapped parallel NOR flash. Back in the days, the software could have been U-boot, something like this. It initializes the hardware, it initializes the DRAM, loads the kernel, starts the kernel from the DRAM, and hands over to the Linux kernel or any other OS kernel. That's how it used to be, but nowadays the bootloader stack grew much more complex. It turned from a single program into multi-component, multi-project affair. Nowadays, the first stage of the bootloader is no longer in some parallel NOR flash, it's in the SoC itself, it's often closed source, it's called the boot ROM. That one loads some sort of a first stage bootloader, which could be TF-ABL2, it could be U-boot SPL. That loads another bootloader stage, which could be U-boot, could be OpTee-OS. That could then load the U-boot, and then that starts the Linux kernel. So it's multi-project thing, it's complicated, but it's all baked together into a single binary, which you call bootloader, and it's part of your bootloader stack. Yes, it is complicated, but it's not as complicated as it's becoming. There is more that is coming. So far, the bootloader stack was running on a single core. The future that is now belongs to safety cores. Basically, some sort of a Cortex-M or Cortex-R starts potentially closed source, maybe open source, maybe free software bootloader program, which could be completely custom written by the vendor that sets up the whole platform. And then when the whole platform is set up, including DRAM, it loads U-boot potentially into DRAM and wakes up the application cores, which are the cores which run Linux, and U-boot literally wakes up when the platform is fully initialized by the safety cores. Communication with the safety cores, that happens via some mailbox interface. So whatever is running on the application cores is completely isolated from the hardware. There is no longer any hardware interaction. But in this talk, I'll go one step back. I'll return to the present, where this whole bootloader stack, which is multi-component thing, runs on a single CPU core. So all these stages in the bootloader stack run on that one core. And I'll talk about this because there are still problems in there, which are then moving to the future part of it as well. Now, since there are multiple bootloader stages, some of these stages may need to protect themselves from some sort of an interference from the follow-up stages. This is done on the CPU side as well as on the bus side. On the CPU side, the protection of the more privileged software, which is running at the very beginning of the bootloader stack, is done using exception levels, which are specific to the CPU core. On ARMv8 CPU cores, ARMv8A and newer, there are 4 exception levels, EL3 all the way to EL0. EL3 is the highest privilege level. This is where the firmware runs, the secure monitor runs. And this is basically unrestricted access to everything on the hardware. It can write any registers, it can set up any sort of protection. EL2 is then the hypervisor. That's also where U-boot is running, bare metal Linux is running. EL1 is virtualized OS, virtualized Linux potentially. And EL0 is unprivileged user application. The idea here is that the highest privilege level firmware can set up some sort of a secure immutables or this kind of protection, and then start the next stage, say, for example, U-boot in less privileged mode, and U-boot cannot access this protected memory. This can be useful if the protected memory contains, for example, code of the more privileged bootloader, or it contains some sort of secrets which the less privileged software is not supposed to access. It is possible to switch between these exception levels from the more privileged one to the less privileged one. This is easy. The software simply decides that it wants to drop exception level, and it drops from EL3 to, for example, EL2. But it is also possible the other way around. But for that, the less privileged software has to trigger an exception. When the less privileged software triggers an exception using either of the instructions, SMC or HVC, the exception is taken in the destination exception level, which for SMC is EL3, for HVC it's EL2, and some sort of a handler for that exception starts running with this higher privilege level. For the SMC, it's usually the secure monitor that installs an exception handler in EL3 for the SMC exception and handles it. Now, what can this be used for is for the less privileged software to somehow trigger the more privileged software to perform some action. Specifically, the less privileged software can request services from the more privileged software, and it's not only an exception that it can trigger, but it can also pass in some registers. ARM has a specification which is called SMCCC, SMC call convention, which defines which registers are supposed to be passed alongside the SMC exception or HVC exception for the secure monitor to interpret it correctly. It says basically that R0 is some sort of a function ID, R126 are parameters for the function, and there are additional specifications, PSCI and SCMI, which define some of the function IDs and what they are doing. In case of PSCI, these function IDs can bring up CPU cores, start them, stop them, reset the system, this kind of stuff. In case of SCMI, this is used to control regulators, enable, disable clock, these kinds of things, pinmux. Now, the problem is that the SMC handler in EL3 is installed very early by the most privileged software on the platform, which is part of the bootloader stack. And both U-boot and Linux kernel may depend on these SMC calls, and especially that the ABI will be stable for these SMC calls. Sadly, with vendor BSPs, this does not always happen, and this leads to a disaster. Problem is, what can happen? The better case is that if you have a system with a stable bootloader somewhere in production, you deploy an update which has a new Linux kernel built potentially against new vendor downstream BSP, then the vendor decides, okay, we will change something here with the SMC interface to better cater for our customer requirements, which is nice because they care for their customers, but in the meantime, they maybe change the ABI a little bit and your system fails to boot, which is not good for you in production because then you have a problem. So you have to recover the system. Hopefully, you already have AB updates, so the system will fall back to the old version of the Linux kernel, which will be compatible with the old bootloader. Good. But there is the alternative, if you also update the bootloader to kind of solve this ABI problem between bootloader and your Linux kernel, and the new kernel doesn't boot, then also your old kernel is unlikely to boot because it depends on the old bootloader ABI, which is no longer there. And your system is basically a brick, not recoverable one. This did happen before. It actually happened between STM32MP13 with their old downstream bootloader and mainline kernel. The SCMI ABI has been different, so the mainline kernel just did not boot on it. And this made me wonder, okay, what can we do about this situation? How can we prevent this ABI problem? One thing obviously would be to teach the vendors that if they once define some sort of an ABI, they should stick to it and never change it. But it seems we cannot really depend on this, so I took an alternative approach. And I realized, okay, instead of doing this, let's bundle together the Linux kernel and whatever blobs provide this ABI, and it will look something like this. So currently the bootloader stack looks like this. The boot ROM is at the very beginning, then there is TFA, which does hardware initialization, that's essentially a BL2. Then potentially there is trusted execution environment, which provides the PSCI or SCMI services on ARMv7. Then there is U-boot, and then there is Linux. They both depend on the services from the T. The change I did was replace the TFA with U-boot SPL. That's because of security considerations. I then started U-boot directly, and from there on, I was able to start the trusted execution environment and Linux kernel in a single fit image together. This way, I have no dependencies on any potentially changing ABI before this point. This doesn't depend on any ABI, and these two things have an ABI between one another, but they are booting together, so that's not an issue anymore. The other thing is, U-boot is a massive piece of code. It's at this point running in the highest privilege level, and it's security sensitive, so we probably don't want that. We want to minimize the amount of code that's running in the highest privilege level. So I enabled Falcon boot mode and was able to boot the T and Linux together from the U-boot SPL. Now, the implementation of the first part is really quite simplistic. I replaced TFA BL2 with U-boot SPL. This automatically gives me the ability to start also or use the Falcon mode afterward. The second thing I had to do was teach U-boot to start OpTee-OS properly on ARMv7A. This gives me the ability to do AB updates because once I can reach U-boot, U-boot has a built-in ability to do fallback boot. It's fully scriptable, so I can select whichever image I want to boot. And then at the end, I enable the Falcon boot mode. I'll show you how to do this as well. Replacement of the TFA BL2 with U-boot SPL. This is actually quite easy because if you have already U-boot running on your platform, and it only depends on some sort of a PSCI SCMI calls, then you already have also the templates of all the drivers which you will be using, and you will be able to use them in the SPL as well. So the first step when doing this kind of thing is you have to look into the drivers, see if some of them depend on any PSCI SCMI calls, and if so, then replace those with direct register writes. And this is mechanical because this is something you look up in the datasheet and then just fill in the register writes into the clock pinmux regulator driver. Easy, so far. The other thing which you will not have, however, is a drum controller driver. So this is something you will have to write for the U-boot SPL to initialize your drum. On the other hand, this is also not complicated because there are very few drum controller vendors on the market. There is Synopsys, there is Designware, there is Renesas, probably a few more. So it is very likely that if you look into the U-boot code base, you will find similar driver for the controller which you have in your SoC already. You will be able to either extend it or fork it, and then you will have drum running. The rest of the SPL porting is integration changes. I did this on the STM32MP13 SOC. And I was lucky that Pinmux driver was already written. It didn't depend on any PSCI CMI, so I could reuse it. Clock driver did need changes, but this was only a matter of filling in the register poking. Drum controller driver could be derived from previous generation SOC, the MP15, with only slight extensions, and then I had to fill in support for new boot image type into MK image. Patches are posted. You can see the result. So if you want to look at how this SPL porting actually happens, that's all of it. That's all the work. And as you can see, the actual implementation is smaller than all the fixes which I prepared up front. So while you are doing this kind of thing, you will probably find also a bunch of things to fix in the code. I have a few hints when doing this sort of an SPL porting, which you should keep in mind. One of them, SPL is size-constrained environment. It's running in SRAM, so you have to be mindful of this. You will not have infinite stack, you will not have infinite heap, and you will have no protection. That means if you allocate too much memory, you will run out of heap. If you overflow your stack, it will just overflow somewhere and potentially write into a register area. That can happen. There is no protection, not at all. The other thing is look at debug UART configuration option in U-boot. This will give you very early on UART output as soon as possible. It's much easier if you can use printf very early to print your stuff than it is to blink some sort of an LED or try to get information out of the SOC in any other way. Lastly, you will be matching behavior of the system to the datasheet, and you will be going back and forth, and you will have to try multiple times some sort of an operation until you figure out how it actually works and what was meant by that one sentence in the datasheet. Find a way to do this quickly. Find some easy way to compile your SPL and start it on the SOC and see what's happening. For the MP13, that's DFU util for USB upload or JTAG OpenOCD. Here is an example how to use the DFU util on the MP13 if you want to start SPL quickly, how to start OpenOCD. Slides will be available so you can just then look at it afterward. OpenOCD has the benefit that it's scriptable in TCL. So you can write quick abbreviations, start SPL, stop the target, load the SPL code into the SRAM, start the SPL. Same thing for U-boot. This will help you greatly, and it will expedite your development very much. Here's an example of how OpenOCD looks like, starting of the SPL. This is the output you will get from OpenOCD. Okay, now, what about U-boot? So when you are finished with porting SPL and removing all the CMI SMSQL dependencies, U-boot and U-boot SPL actually shared drivers. So when you did this work for the SPL, you also did this work for U-boot. That means at this point, you should also be able to start U-boot just like that. So I will move to the next section, which is start OpTee-OS from U-boot. Before I get into it, OpTee and OpTee-OS are two different things. OpTee is a bigger project which provides the whole trusted execution environment and all the stuff around it. OpTee-OS is only one component from the OpTee project, which provides the runtime for trustlets and which provides the services to the non-secure world. There are also trusted applications which are not part of the trusted execution environment. These run in the secure world on top of the T. They are provided by developers of these trusted applications. There is OpTee-OS client, which is provided by the OpTee project. It provides the supplicant client to communicate with these trusted applications. There is a test suite and so on. But in the rest of this talk, I'll talk only about the OpTee-OS, which is the library/runtime which provides the services, because that's the interesting part. The OpTee-OS library/runtime is installed very early on, either by TFA, BL2, or it can be installed by U-boot SPL. It has to run very early on because it has to install on ARMv7 its own secure monitor handlers. On ARMv8, there is a slight difference that the secure monitor is external to the OpTee-OS, so the handlers are installed potentially by TFA, and OpTee-OS is only loaded into memory, and it doesn't install anything on its own. Right. To invoke the OpTee-OS, this is called or triggered by some sort of an event which is coming from the non-secure side. Often that means Linux kernel wants something from the OpTee-OS. It does SMC, the OpTee-OS handles it somehow. It doesn't have any sort of internal scheduler, so it doesn't really behave like a separate operating system would be running on your core. It's event triggered. On ARMv7A, the OpTee-OS has its own secure monitor, and starting the OpTee-OS is actually very, very simple on v7a because it does all the work for you that needs to be done to install the secure monitor. You really don't have to do much there. To start OpTee-OS on ARMv7a, it's basically a matter of picking up the right file because when you build OpTee-OS, it will generate multiple binary files. There are some which have some sort of a header in front of it, some are ELF, executable, loadable format, these kinds of things. I picked the traw.bin because this is literally built of OpTee-OS, which is linked to a specific address without any headers, without any other stuff. This file has to be loaded to the link address because it's linked to that specific address. And then it is actually enough to jump to it and it will do something, but it expects 5 registers to be set up correctly to actually do something meaningful. There are 2 registers which have to be 0. CPU registers are 0 and R3. R1 and R2 are passed through to the software that runs after OpTee-OS, and link register has to be set as well. Because the link register points to the next stage to which OpTee-OS actually returns. So when OpTee-OS does its initialization, when you jump to it, the initialization will look something like this. It does its own internal state initialization, initializes its drivers. When it's done doing all this initialization, it triggers the secure monitor on ARMv7a. The secure monitor actually signals to the OpTee-OS that the initialization completed, and then it will pop stack and attempt to return to whatever was in the link register. And whatever is the OpTee-OS returning to, this will be running in non-secure mode. Usually that's going to be Linux kernel entry point. Here is an example of starting the OpTee-OS from OpenOCD. That's here on top. It's yet another thing. Load the traw bin to an address, jump there, do some stuff. At the bottom, same thing, done using U-boot. I couldn't write to the address de blah 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 directly because that was protected by trust zone at that point, so I had to copy the data in there. But otherwise, you can see how the OpTee-OS is starting here. This is with debug level 4, so you get some debug prints there. And then it hangs because the registers were not set up, so it cannot really continue anywhere meaningful. Now, instead of hacking this somehow in U-boot to set up these registers, I would like to use something else. And I would like to introduce you to FitImage first. So FitImage is a multi-component image type based on device tree. What this means is that it can serialize multiple files into a single file. Each file has some sort of additional description attached to it, and this all gets bundled into one single container file. The source description for the FitImage looks like this. It's based on device tree, so the device tree syntax should be familiar to. There is an images node. Each subnode in the images node describes one image which is bundled into the device tree. There is reference to the data which are going to be bundled into it, type of the image, where it's supposed to be loaded, the entry point, and so on, checksum, configurable. Another image, which is a device tree. That's one part of the fit image. So it can just serialize like multiple images into a single file with metadata. But there is another thing, which is configurations. That's another half of the fit image. The configurations put all these images in the fit image together in some sort of a meaningful, configuration. It allows the user to select which of the images in the fit image fit together, and it allows the user to boot this specific configuration. When this happens, like for example here, there is a Linux kernel 1 that's a reference to the kernel image, and FDT1 that's a reference to the device tree. When user would boot this one configuration, which is actually default, U-boot would pick out the Linux kernel 1, place it at the right location, pick out the device tree, place it at the right location, and boot this combination of images together in the right order. That's what fit image is about. And when this fit image is assembled, it just produces a single file which U-boot can boot. OpenEmbedded can generate fit images since 10 years. U-boot can handle them. The integration is already in place, so that's that. Luckily for me, the OpTee-OS support, the image type for OpTee-OS is already in the fit image, so U-boot also knows that there is something like an image type T here. And I could simply bundle the T raw into the fit image, reference it in loadables, and simply let you would boot this kind of a fit image, which would then contain the Linux kernel, the device tree, and the OpTee-OS in this one single bundle, and generate the fit image like this, and it doesn't work. So I was debugging this, and I found out that the OpTee-OS implementation, the OpTee-OS boot implementation in U-boot was meant for ARMv8, and so I had to patch the boot code a little bit to detect that on ARMv7, if the OpTee-OS is loaded to a certain location, then I need to make a note that this happened, and when booting the Linux kernel, I had to add a little bit of a glue code that instead of directly jumping to the Linux kernel, would set up these 4 registers needed for OpTee-OS, the link register, and jump through the OpTee-OS to the Linux kernel. Patches are posted. The jump handler is completely banal. It's just a little piece of assembler code. The changes to the kernel boot code look like this. One potentially interesting thing is this fit loadable handler macro, which allows you to define for specific fit image types shreds of code which will somehow get executed when such a loadable appears in the fit image. So I used it to make a note that the OpTee was loaded, and then when the system was just about to jump to the Linux kernel, I invoked this assembler code, jump to the OpTee. The OpTee runs, it looks like this. Fit image gets loaded, U-boot prints all kinds of information about the fit image, kernel, device tree. OpTee-OS actually got loaded to the E location, and then U-boot is just about starting the kernel, and OpTee-OS printout shows up in the output, and Linux kernel starts booting, and Linux kernel can communicate with the OpTee that just got started. Patches are posted. One word of advice when it comes to the OpTee-OS, keep in mind the OpTee-OS is security-sensitive code. It is important to configure your trust zone correctly, otherwise OpTee-OS may have issues or it may be unsecure. The trust zone configuration is done, this is platform specific. It's mostly a matter of configuration of bus firewalls, and this is something you will have to figure out based on your SOC datasheet. On the MP13, it was a matter of configuring the ETZPC and TZC, but this is going to be called something else on your platform. On IMX, it's called AIPSTZ, for example. I'm sure you can find it in the datasheet. It will be somehow branded Trust Zone. So there is that. Okay. Let's talk about AB update. So the current state, the current situation we actually have right now is that we have uboot SPL, we have uboot, capable of booting Linux kernel, device tree, and fit image together from one single file, which is stored somewhere in the file system. Now, uboot also has the ability to do fallback boot. That means if some sort of a boot counter overflows, it will run some sort of a different boot script. And this is already part of uboot for 20 years. It's been there since forever. And with these tools, that means OpTee-OS Linux kernel and device tree being in single file, and the ability to start one or the other fit image from some sort of a storage, it's possible to implement AB update whichever way you actually need it to. And the thing is, if the fit image fails to boot and watchdog triggers and uboot detects this, it can simply boot another fit image just like that, which could be the recovery fit image, which will have its own copy of OpTee-OS, which will have its own copy of device tree and Linux kernel. It will boot all these things together, actually, and there is no danger that the B copy or the recovery system will have any sort of ABI incompatibility because you are booting essentially the old OpTee-OS copy at that point. There is no shared OpTee-OS copy which would be providing any one ABI. And that's how it is. That's how it can work, I believe. Now, so far, I was talking about keeping uboot in this boot pipeline or in the bootloader stack, but there is one more problem with this. The problem is uboot has scripting capabilities. uboot has network stack. uboot has USB stack. It has a lot of stuff in this, and that makes it massive attack vector. With this setup, which I demonstrated before, uboot would be running with the highest privilege level on the platform, and that's potentially not going to sit well with security-minded people. It's not a good idea, basically. But uboot had for a very long time support for booting these fit images directly from the SPL stage. And the SPL stage on the MP13, even with the OpTee-OS booting support and all that, is like 100 kilobytes, so it's much smaller than the uboot, which is much bigger. And I would like to show you how to actually enable what's called the Falcon boot mode, which is the name of booting these fit images directly from the SPL stage. In the next slide. One more thing about the Falcon boot mode. Yes, it can boot fit images. The fit images can contain Linux kernel, device trees. It can also contain TFA-BL31. So if your BSCI provider is TFA-BL31, you can boot it as part of the fit image from the SPL stage. It can boot the OpTee-OS from the fit image from the SPL stage. And yes, it is capable of AB switching as well and fallback to actually start uboot fit image. So the Falcon boot mode is also capable of selecting between booting Linux kernel directly or booting some sort of a fallback uboot fit image for factory manufacturing, this kind of stuff. To enable the Falcon boot mode, define this configuration option, SPL OS boot, make sure fit image support is compiled into the SPL. And besides that, you have to define configuration options which are specific to the boot media which you are going to use. The SPL is a very small piece of code. It's not so flexible as uboot. That's why a lot of things are hard-coded into the SPL. In this case, where the uboot is, on which sector, on SDMMC in my case, and where the kernel is in the SDMMC, in my case. Right. I have 2 slides left. The SPL start uboot function, this is the selector between boot uboot from this address or boot the kernel from this offset. Now, I had to modify the function which starts the Linux kernel in SPL as well to handle the OpTee extras. I could reuse most of the work I did in the uboot, and the patches are again posted, so if you want to look at it, the slides actually have links to all these patches, so you can look them up. Finally, AB switching. This has to be hard-coded into the SPL, override this board-specific function in your board port, and select which of the A or B copy of the Linux kernel you would like to boot from whatever offset in the MMC. So it's, again, a matter of implementing one function in the SPL. So to wrap it up, TFABL2 can be replaced by SPL. This gives you automatically the Falcon boot support, and also it's not so difficult. OpTee-OS can be started from uboot. It makes it easier for you to experiment with OpTee-OS. If you are doing OpTee-OS development, you can start it from uboot, maybe via TFTP, makes it easier, and also avoids any dangers of ABI incompatibility between the Linux kernel and the OpTee-OS bootloader blob. And if you are then deploying this stuff in production, then I would recommend you look at the Falcon mode, boot the FID images with OpTee-OS directly from SPL, which removes uboot as the attack surface entirely from the bootloader stack and improves platform security. Thank you for your attention, and if we have time for questions, then yeah.
We could take one question, I think, before we move on. If there's any questions? Otherwise, we can badger Marek at the restaurant
otherwise
tonight.
you can just reach me here. I'll be here all 2 days. So. There we go.
Okay. So I know it's not a good idea, but what about if you don't need OpTee?
Say again?
Here. What about if you don't need OpTee and you directly Falcon boot to Linux? How much time would that cut from boot time? Is it possible nowadays to?
It is possible to directly boot Linux without the OpTee-OS, yes. This is what the Falcon boot was meant to do, actually, at the very beginning.
Yeah, but do we know it works now with ARMv8?
On ARMv8, you will most likely have to start at least TFABL, well, either SPL or TFABL2 and BL31 for the PSCI provider, because on ARMv8, you definitely do need PSCI. The Linux mandatorily depend on that, on V8. You would actually thus implement PSCI provider as well, so you could potentially try to use this. On Renesas, there is a fallback PSCI provider in uboot, so in case there is no other PSCI provider, uboot will provide basic PSCI provider for the platform so the Linux kernel can boot.
Can you include that in the kernel instead?
Say again?
Can you include that in the kernel as a...
With the PSCI?
Yeah.
I think there will be some opposition to this.
I know.
On ARMv7, this is how it worked. On ARMv8,
No, it's not going to happen.
send patches and see what happens, I would say. I'm not the guy who is going to decide the fate of this patch set.
Okay, thanks, Mark.
Sure.